doesn't look like. Um, so um, axions is a very rich topic, and we could have spent all 5 lectures just talking about axions if we so chose. If I so chose, I guess you didn't really have a choice in the matter. Um, and so we're not going to be able to do justice to the whole topic, of course. Um, and there's many reviews. There's many recent reviews. There's one review per year on axion physics. So I encourage you to go and look at those reviews for topics that we won't be able to cover. But I thought I would give you some qualitative features of axions and axion models that maybe helps you in navigating this intricate graph of axion papers, and also the stuff we've been talking about, spending so much time on quantum mechanics of the theta angle and so on. Hopefully, gives you a solid foundation for then to build up model building on top of that for axion models. Okay. So the rough plan is to first just introduce axions. We talked a little bit about this yesterday. What is the terminology, which if you're not an expert or not working in the field itself, could be confusing. People use axions to mean different things in different papers. The one aspect I would like you to take with you is that axion couplings are quantized. This may or may not have been obvious to people um, when they were working on axions back in the 80s when they were first invented. But certainly in the past few years, this has been emphasized much more, and the consequences of quantization of these couplings has led to a lot of the recent developments in axion physics. I'll tell you a little bit about QCD axions, the axions that are really our job to study when we're talking about the strong CP problem. So these are axions that are probably some of the most compelling models of new physics that are actually experimentally accessible over the next decade. So if you really ask me to bet some finite, not infinite, finite amount of money on what we'll find in the next decade, so in fundamental physics, would say the QCD axion. And there's a model for the QCD axion, which just for the structure, it's useful to just know, which we'll talk about. Maybe not all of them. And finally, I want to highlight one particular class of models called extra-dimensional axions, which even within this class of the QCD axions probably is a compelling candidate of axions all to itself. In string, you might have heard this statement that in string theory, there's a lot of axion candidates, and the toy example we will study for the extra-dimensional axion will be just a prototype for how axions come about in string theory, which is a higher dimensional gauge theory. Okay, some aspects that we will not cover, but I encourage you to look at. So one thing that I would really have like to cover in slightly more detail, but so this is not the phenomenology or cosmology of axion physics. So some aspects of cosmology you've been hearing about from Ed. They are excellent candidates for dark matter. They naturally have the possibility of forming topological defects in the early universe, and have associated signals with that and associated physics with that. That's interesting. They are very interesting in astrophysics. If they're dark matter, then they could interact with the standard model and give us signals either in around interesting objects like neutron stars, or themselves make axion stars. So all of these things part of these things you've also been listening to in Ed's lectures. There's also a vast experimental program for axions in tabletop experiments. There's cavity experiments that look for axion-photon couplings. You can look for axion in fifth force experiments. So there's a really, I'm not exaggerating when I say that we could have spent all 5 lectures talking about axions and exciting physics, both theoretical as well as experimental in axion physics. So this is an aspect that I encourage you to look up more, and some reviews do a really good job of going through the phenomenology of axion physics, so that hopefully we'll cover that gap. Another aspect that we will not cover, which is potentially worth visiting, is model building aspects. Um, for QCD axions, but in general for axion-like particles. Oh, sorry, I should say, in phenomenology, there's also very interesting signatures of axions around black holes called superradians, and uh, and for yeah, so that is itself now a small field of trying to understand superradiant signals of rotating black holes in theories which have axions. All of those would super exciting topics, well worth looking into. So there's model building aspects of axions. For example, to just give you a few buzzwords, you can get heavy axions. Um, you can get heavy axions. What heavy means, maybe when we talk about the QCD axion, I'll say, but you can get heavy axions using either a Zn symmetry, heavy QCD axion, either using a Zn symmetry or small instantons. And some aspects of model building people have been looking at over the past few years use these features. The idea is that the QCD axion we'll see is relatively predictive. It tells you it lies in some parameter, in a line in some parameter space. And the question is if we that's a very nice feature of the problem. Like, it gives a target for experiments to reach. But the question is, if we've completely, let's say we completely excluded the QCD axion on that line, have we completely excluded the mechanism, or is it easy, possible, or impossible completely to get out of these predictions for the QCD axion? And so some of these model building ideas are trying to explore how robust is this prediction for the QCD axion to lie on this line that we will talk about in a few minutes. There's also light axions. So you could also ask, can you be lighter than what this line in the parameter space predicts? And also, again, there's models, some Z using some Zn symmetries, which let you make models with light axions. These are interesting because, well, I'm saying this a lot, so maybe let's draw a picture. Typically, in a phenomenological plot in axion physics would look something like this. There's some parameter called the axion decay constant that sets the coupling of axions to various things, including photons, maybe nuclei, and the constraint looks something like this, very roughly in this plot. There's some constraint coming from stars, from tabletop experiments, from supernovae that rule out very large couplings, but then eventually at some mass they peter out. The typically plots look like this. Maybe there's some cavity experiment that looks like that. And the QCD axion is a line in this plot. So let's say this is maybe is a line on this plot, and it's a target which we're trying to hit. So these ideas of model building are whether we can go to the right of this line or to the left of this line, so heavy or light axions. And if it's generically possible to get heavy axions, then it might not be sufficient to hit this line to rule out the QCD solution to the strong CP problem. Light axions, if it's generic to get light axions, then it's exciting because there's a lot of experiments who live in this region. They don't go down all the way down to the QCD axion line, and they would actually have a chance to detect the light QCD axion, right? So that's the motivation for trying to explore how hard is it to do models of beyond the standard KSVZ type models or composite DFSZ type models that we'll build. There's another mechanism that goes by the name of clockwork, which was trying to see whether we can go this direction. Can you increase the coupling beyond the standard values of the coupling that QCD axions are supposed to have? And again, people were trying to build models which achieve that. So I won't advocate spending all your time just trying to build arcane models for the QCD axion, given that the QCD axion itself works and hasn't been excluded yet, and so it could be just the simplest possibility is the most compelling one. But it is worthwhile to explore how robust is our prediction, this QCD line that we talk about. How strongly do we believe that the QCD axion has to lie on this QCD line? Okay. So we won't have time to go through these model building aspects, but again, they're instructive. They're instructive in their own right to tell us how much wiggle room there is in what we expect the QCD axion to look like. And it turns out it actually requires a reasonable amount of structure. It's not that easy. And the models don't look very compelling once you actually try to build them. It's possible to build any of these models, but none of them look super compelling. And so really the QCD axion line is probably the primary target for us in the next few years. So that's the plan. Any questions about the general picture? Okay. So what is an axion? We're increasingly asking very basic questions in particle physics, so it's good to ask basic questions. What is particle physics? What is an axion? This is various people would disagree in their use of the terminology of what an axion is, and like any definition, the whole point of nomenclature is its utility. Any definition or nomenclature is whether it's useful or not. So, what is a useful notion that lets us call some particles axion and some particles not axions? So, I think these features are probably true for any kind of axion people talk about. If your particle doesn't have these features or your field doesn't have these features, it'll be really strange to call it an axion. So the first is compactness, which is that the field space is a compact space. For a single axion, it's a circle with some periodicity. So just like our particle on a circle, this field now lives on a circle, and the field is identified with 2 pi times Fa itself, and this is called the periodicity of the axion. There's almost always an approximate shift symmetry, global shift symmetry. So again, as I've been emphasizing, this identification is a discrete gauge symmetry of the axion. And there's an approximate global shift symmetry where the axion shifts not by 2 pi Fa, but some other real number. And this symmetry is a global symmetry, and it's not expected to be exact, but there's an approximate shift symmetry. So that just tells us the axions are light. And are what are called pseudo-Nambu-Goldstone bosons. The idea is that we have some approximate global symmetry which is spontaneously broken. If that is the case, then we expect not exactly massless but light Goldstone bosons. And most symmetries that we encounter, most global symmetries that we consider are compact symmetries. So there's U1s or SU2s. We can talk about non-compact global symmetries, but they're rare. And so the typical usage of this is in the context of a compact global symmetry. When you take something like a U1 and you break it spontaneously, the Goldstone boson lives on a compact manifold, right? So these ideas are connected to each other. For most global symmetries that we consider, The pseudo-Nabu-Goldstone bosons that we do get are actually compact and live on a circle or on a compact manifold. Just like pion, for example, the other example of we won't call pions axions, but you could get away with calling pions some kind of axions because they're associated with some compact symmetry breaking. They're like phase of some a phase of some operator. They're like they have approximate shift symmetry. They're pseudo-Nabu-Goldstone bosons, so they check all the boxes you would ask axions to. Um, and and there's a parallel that we will keep drawing, where we think of axions in analogy with. Oh, sorry, another thing that is relevant for something to be called axion is its coupling to gauge fields. So a typical, almost anytime you think about an axion, you're thinking about a coupling of the axion with something like FF tilde or GG tilde. If you don't have these couplings, it would be very strange to use the term axion. I mean, nobody can stop you. It's a free archive is free, so you can write whatever you want. But yeah, people would be puzzled if you don't actually, if you're thinking of axions which are not coupling to gauge bosons like this. Okay, so these are sort of generic features that you would ascribe to something called the axion. Question. Um, yeah, I mean, I guess if you didn't have this, then you would really just call it a PNGB. But if you had this, calling axions PNGB is also totally fine. So they're not mutually exclusive terms. You call pion PNGBs, but pions have pi FF tilde coupling, right? So instead, certainly they're not, the terminology is not clean and formalized. But if you don't have this, calling it axion would be a bit strange. But it's, you know, if you define it carefully enough, nobody will really complain. So when you encounter the word axion in the literature, you should have in mind, the first picture you should have in mind is some particle, some field which has these properties. Okay, question, sorry. Yes. There's none of this is requirements, but if you have a spin one particle, you would not call it axion. Or yeah, you could, but you would have to really explain yourself why you're doing that. Sorry, which one there? Yeah, so by heavy, so because the axions is not quoted, the heavy really means that it lives to the right of this line, the right of the QCD line. So the shift symmetry is approximate. So these are light in the sense that they are microelectron volt particles where the physics, the spontaneous symmetry breaking associated with them is 10 to the 10 GeV, 10 to the 12 GeV. So they're light. So they are very good approximate global shift symmetries that we're talking about. But they could be heavier. So instead of 1 micro eV, there could be 100 micro eV, which makes a huge difference for the experiment. But certainly, they're still PNGBs by a huge margin. Any other questions? Okay. So one aspect that is also a slightly more qualitative physics aspect of axions that I want you to keep in mind is that to think about axions in analogy with the photon in some sense. So the axion, you should sort of think about like you think about the photon, like a gauge field of some kind. Okay, you can make it slightly more formal. You can think about gauging a -1 form symmetry, and there's some people who have, for example, Matt Reese's lectures puts forward this point of view. But at least qualitatively, when you see a photon field, it's not just any scalar field. You can't write down whatever you want with it. We think, oh, there's gauge invariance. We have to be careful. We should maybe package it in F. So we should be careful what we couple a photon to. Can't do whatever you want. You should have the same kind of feelings towards the axion field when you see it in the Lagrange. Okay, and the crucial bit being that the axion has this discrete gauge symmetry that corresponds to these large gauge transformations that we talked about for the photon. So some part of the gauge transformations of the U1 gauge field photons, the large gauge transformations, are exactly the gauge transformations of the photon itself, are the gauge transformations of the discrete gauge transformations of the axion itself. And this will become even more precise as a connection when we talk about the extra dimensional axions in the second part of the lecture. So, for example, A itself is not a gauge invariant operator, obviously. Under a gauge transformation, it goes to A plus 2 pi. Just like capital A itself is not a gauge invariant operator, right? So d mu A is perfectly fine. Just like f mu nu is perfectly fine. And in differential form notation, this become even clearer. D mu A corresponds to something like dA. So the exterior derivative of a zero form dA, and f mu nu corresponds to something like dA, d capital A, the exterior derivative of a one form. So in some sense, A is a one form version of the axion, which is a zero form field from this point of view. Okay. Again, these are not formalized definitions. We can make them formalized, but it's good to keep this in mind. So A not being a gauge invariant operator, you would say, well, we should maybe make our Lagrangian with the gauge invariant operators d mu A and not put A by itself. Then maybe our action would not be gauge invariant, right? And you would say, you could naively, you could also say the same thing about capital A. You could say, well, capital A is not gauge invariant as an operator, so I shouldn't write down terms involving just A. I should only write down terms just involving f mu nu, and that would, of course, not describe our universe. So what we do is, when we write down the photon field in the Lagrangian, we couple it to very specific kinds of objects. So when you write down the photon field, we write it down in the action. We integrate the photon field and in coupling it to a current, and we impose that the only possible thing that we can couple to is a current that's conserved exactly. Right? And this is a consequence of asking, well, A is not gauge invariant, but if I do a standard gauge transformation, A mu plus D mu alpha, this extra gauge transform term doesn't contribute if the current is exactly conserved. Right? So already just knowing that A is not gauge invariant tells us we can't couple it to any old thing. It has to couple to conserved currents. In fact, we can go a step further, and we can also prove that the electric charge is quantized. It should couple to something that is quantized. Similarly, we'll find that small a, so if you write down just a term like this in the Lagrangian, you would worry that this term doesn't look gauge invariant. If I do a going to a plus 2 pi fa, this term isn't gauge invariant, and so it should put restrictions on what kind of couplings I can write down in this theory, right? So indeed, if your action is this, the action under a going to a plus 2 pi, so let's call this coupling what should we call the coupling? Let's call this coupling capital, this curly a. Okay, so I have a coupling which is curly a integral d for x. We can put in factors of alpha s and 8 pi's and fa and so on, but let's just let's not make them explicit. Those factors are there. Okay. So under a plus 2 pi, this goes into 2 pi a g tilde. So the action doesn't seem to be invariant under gauge transformations, which seems to be a problem. We typically want our action to be invariant under gauge transformations. But actually what we want is not necessarily the action to be invariant under gauge transformations. We want our path integral to be invariant under gauge transformations. And the path integral actually does not contain the action as a weight. It contains e to the is as a weight. So we don't say s should be gauge invariant. We say e to the is should be gauge invariant. Which means S, under gauge transformations, S can go to 2 pi S plus 2 pi n. Right? That ensures that S is gauge invariant. So this is a whether whether it was made explicit or not, this is always the case, that the actions we consider whenever we have any kind of gauge field are typically not gauge invariant. They are only they're only e to the is is gauge invariant. This is also true if you do a large gauge transformation for the photon. You'd find the action actually shifts by 2 pi times n. Okay. And so what this tells us is that this quantity d4x, the coupling of the axion to gg tilde, should be 2 pi times an integer in order for the path integral to make sense. Okay. Is everyone happy with that logic? Okay. It's not emphasized, but it's really true that the quantization of various things comes about as a result of asking for this subtle difference between S being gauge invariant versus e to the is being gauge invariant. Good. We do know that the gg tilde is actually a quantized itself. It's a total derivative, so it depends on the surface of your space-time and the topology of your space-time, and in particular, it counts the winding number of your gauge field on space-time. So this is analogous to, by the way, what we had, dt q dot, which we said was delta q, which was some winding number as you go around the circle in a particle on a circle. Okay, this gg tilde just counts the winding number. So this gives us some, and there was a 2 pi here. So that tells us that a should be an integer. Again, we can put in some the standard normalization factors for canonically normalized field if you wish. So a would be an integer in some units of alpha s and 8 pi or whatever. But the crucial, apart from that overall normalizations, the crucial bit is that you can't write down any old coupling of axion to gauge fields. You have to write down couplings of axions which are quantized. So there's a discrete choice of couplings that you can get in axion gauge. Okay, which is not a priori obvious, and whenever we have quantized couplings, we have much stronger predictive power. Of course, if we can figure out what the unit of quantization is, then we have to measure 1 or 0. It's not a sliding scale where it could be arbitrarily small in some units. Okay, any questions about this? Yes. Very good. So the question is so we could write down a coupling of the axion to photons. We can write down a coupling of axions to gluons. I chose gluons here because we know for sure that gluons have instantons even on Minkowski space, and so integral gg tilde is an integer, right? Which is what we use to say. If you talk about axion couplings to photons, so let's write it down here. So we're talking about AFF tilde, and again, one of the things we would want to use is this equal to is it equal to some? Can it be some non-zero integer? If this is always 0, then this gauge transformation doesn't produce any effect, right? So the argument in the case of the photon requires an extra bit of input or subtlety, or however you want to say it. That, as we said when we talked about the Witten effect, that while on Minkowski space, there's no abelian instanton number, so there's no effect of the theta term on Minkowski space. As soon as you have non-trivial topology, that non-trivial topology could come from either the space-time, you put the theory not on Minkowski space but on a torus or in a 4 torus or whatever, or you just have magnetic monopoles around. In all of those cases, this now has a physical significance, and it has to be quantized if your photon is a U1 gauge field. So there's sort of you could ask whether, well, maybe I don't have magnetic monopoles. Maybe I never want to put my theory on anywhere except Minkowski space. So can I get away with it? At least in theories of quantum gravity, it would be probably very hard to do so. Quantum gravity gives you topology changing processes. So you can just, if you want gravity to, your space-time to be dynamical, you probably want to include all topologies. Or you can have magnetically charged black holes. Magnetically charged black holes would produce the same effect, same Witten effect, and make this, again, integer quantized. So even though it's not totally clear on Minkowski space, this is also integer quantized, and if saying all those words that I said. And so then you also expect the axion photon coupling to be integer quantized. Any other questions? I should say, maybe I'll get to it, maybe I won't. So in the standard, just because I said something which has there's an interesting story behind, in the standard model, QCD axion model, the usual way we write down the axion photon coupling is something like this. And there GA gamma gamma is, you don't quote me on factors of 2, but I guess you don't put FA here. Okay, so there's a general, I gave you this very general argument that couplings of axion to photon should be quantized. On the other hand, if you just work through the QCD axion example and get to the end of it, canonically normalize everybody, get rid of every other field in the Lagrangian, integrate other pions, just write down the axion photon Lagrangian, the actual coupling you get has some bit that satisfies this quantization that I told you about, but it also has an irrational component, which seems to be in conflict with what I just told you. It's not in conflict, so that resolving this actually is an interesting story. But I just wanted to give you this as a that you don't go away thinking that there's some the answer has to be quantized at the final step. There's actually, in the real world, the answer has this irrational component as well. This arises from, very loosely speaking, mixing with the pion, but the actual story is the actual story of how this argument I just gave you and that fact about the QCD axion coupling to photons, how these are compatible is actually a nice, interesting story that if we get to, I'll tell you, but if we don't get to, I didn't want to leave you with a false impression about the final answer. In particular, in the QCD example, that 1.92 dot 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 is calculable, completely model independently calculable, and all the model dependence of what BSM physics the axion belongs to is in these quantities E and N, which are quantized quantities. So again, there is a quantization of axion couplings, which just shifts by due to its mixing with the pi 0 by a completely calculable amount. So the amount of predictive power that we still have for axion photon couplings is not changed. It's still parameterized just by integers. Oh, okay. So maybe the next thing I did want to talk about was the QCD axion. Are there any questions about quantization of axion photon couplings? Okay, so with those generalities of how to think, what object the axion is. It's this weird scalar version of a gauge field, has restrictive couplings to other gauge fields, has this large gauge transformation, has quantized coupling. So it's not just any old phi to the fourth theory that you can write down. It's a rather special kind of scalar field. Um, let's look at its applications for the problem at hand, the strong CP problem. So if you remember, we said, when we talked about the standard model, we said the SU2, theta angle could be rotated away just by doing a chiral rotation on quarks, and the baryon number being anomalous with SU2 tells us that we can shift the theta angle. So we said theta SU2 can be set to 0 by U1 baryon rotation, um, because U1 baryon was a symmetry, is a symmetry of the standard model Lagrangian, but it's up to anomalies with SU2. And so we can use that anomalous symmetry to get to rotate theta to 0. And we said that we couldn't do this for theta QCD. So this is not for theta strong. So how many people remember what we talked about in the ancient history of 2 days ago? Why could we not do it for theta QCD? You have a take? So we said we don't. You said we don't have the symmetry. So we don't. Yeah. So one possibility was to use a discrete symmetry. You're right. And we said, well, CKM violates that, and then but we can try to build a model build around that. So that gave us the hint to look at all these discrete symmetry solutions. Can we try to find a anomalous? Can we try to find an analog of this anomalous U1 baryon that will give us the same thing? So imagine I had some symmetry. Let's call it a PQ symmetry. And I said this is anomalous with QCD. This is a symmetry of my BSM theory. It's anomalous with QCD, and it just gives me, using this symmetry, I can rotate away the theta strong as well. So what is wrong with this guess? That why can I not write down? We said something why we could not write down this. The symmetry, there's not one in the standard model, but there's not even one in any BSM theory you could write down. There's a PQ symmetry that you could rotate away with the theta angle with. Surely some of what I'm saying is going in. It's not, can't be that. You don't have to be correct. You just have to say something. Maybe we'll play the 1 minute game. Any other takers? Sure. Yeah. So we'll get to the how the QCD action solves it. The question is, can I have a BSM symmetry where I can have a unbroken PQ symmetry, which rotates away the theta angle? Here we had an unbroken U1 baryon symmetry, and that we just got rid of the SU2 angle with no low energy consequences whatsoever, right? So that's what you'd like to ask. Oh, that seems interesting. They have nothing to look for, no low energy consequences. I just had some U1 baryon symmetry that happened to be anomalous with SU2. I just rotate with that symmetry, and I get rid of theta angle, no experimental consequences. So can we do the same? Can we find some theory which has some way that we have a PQ symmetry that's unbroken, and no low energy consequences, and rotate away the theta angle? And we said that's impossible. So why is that? There's too many negatives in your question. So, did you have a? Indeed. So what we said was that uh, if uh, if we want something to be anomalous, so we want this U1 PQ to be anomalous with QCD. That can only be anomalous if we insist that PQ is unbroken and QCD is unbroken, which we would like very much. Then that would imply that any fermion that contributes to the anomaly between them remains massless. Okay, so we tried the massless up quark solution. That would have been an option where SU3 remains unbroken. There would be a PQ-like symmetry that would remain unbroken, and we get a massless quark. And that didn't work. Lattice tells us no go. So now if we wanted to impose use any version of the solution where PQ and color was unbroken, we would end up with massless quarks, new massless colored fermions, which are probably a bad idea. So then what option is left for us is to actually not have this. When SU2, why don't we get anything massless left over? Because SU2 weak is spontaneously broken. So we have quarks and leptons which are massless until SU2 is broken, and they get mass only through breaking of the SU2 symmetry, and so they can continue. They contribute to the anomaly because their mass is a effect that breaks these symmetries. We still don't want to break SU3 color, so the only option left to us is to explore, can we have a system where U1 Pechequin is spontaneously broken, and that's the way we get rid of the anomaly. Okay, so naturally when we try this option that is already presented to us in the standard model, we find that the kinds of model we're looking for is U1 Pechequin is spontaneously broken, and it can be broken at some whatever scale we want, but there is a low energy consequence. We get a pseudo-Nambu-Goldson boson, which is the QCD axion. Okay, so that's sort of the little bit of detective work that might have led you to the QCD axion solution, saying what are the options to actually get rid of theta QCD. It actually turns out that the only option is to have some in this kind of solution. The only option has to have a spontaneously broken what is called a Peche-Quinn symmetry by Peche and Quinn, who first thought about the symmetry. And then Weinberg and Wilczek showed that there actually needs to be a light degree of freedom called the axion in this theory. Okay, and in the this by itself is okay. Yeah. So in terms of the low energy EFT, so just below any heavy physics we write down, just in the standard model Lagrangian, we would have just the theory of one extra axion plus the standard model fields. We can even go below the QCD scale, and what we'll get is a theory of axions and pions. Since I just wanted to give you that EFT because it's interesting. And does shed a little bit of light on this quantization of axion-photon interaction that I talked about. And let's keep the pion in. We could also, because the axion is, eventually we'll find that for any allowed values of the axion mass, the axion is so much lighter than the pion, we can actually integrate out the pion as well and just work in an axion-photon Lagrangian. But let's keep a pion in for a second. And the effective theory you get is and yeah, so how do we find this effective theory? This effective theory is essentially the same way we found theta dependence in the chiral Lagrangian. Axion in the, yeah, maybe I should write that first, sorry. Before, above the scale of chiral symmetry breaking, the effect of this U1 PQ spontaneously broken is that it adds to the standard model This is n. Okay, so when we have the spontaneous symmetry breaking of the axion, that's roughly at the scale given by this periodicity of the axion Fa. This is the statement that if you have a wine bottle-like potential and the Web is order Fa, then the radius of that circle, the periodicity of that circle is 2 pi Fa. Right? So this Fa parameterizes the scale of spontaneous breaking of the symmetry, and typically in any realistic model, this is 10 to the 10 GeV or higher. Something between 10 to the 8 GeV and Planck scale is the typical phenomenologically relevant scale for Fa. If the U and PQ symmetry had anomalies, then when you integrate, I'm going to talk about in a second. The anomalies have to be reproduced in the low energy theory, and so these terms can be used. We can use anomaly matching to deduce the existence of these terms, where N and E characterize the anomaly with QCD and photons respectively. And if you calculate an anomaly diagram, you'd see that the anomaly is actually proportional to electric charge squared. So a typical anomaly diagram might look like this, where there's a axion here and say photon here, and the anomaly itself would go like something proportional to the charge of particles running in the loop. And so indeed these coefficients are, when you can do these perturbative calculations, in a given UV theory, you can just calculate these quantities in a Feynman diagrammatic way, and you will indeed find that these are quantized coefficients once you put in the factors of alpha and 8 pi or whatever the standard canonical normalization is. Okay, so indeed, if you're far above the QCD scale, this argument of quantization we're talking about holds even naively, and when you do perturbative calculation, that comes out in this particular way. So that's the theory below the scale of U1 PQ breaking. If you go below the scale of QCD, then we go from the standard model QCD description to the chiral Lagrangian, and that's the description of the axion pi Lagrangian, which again you can use this Lagrangian plus the QCD Lagrangian to match on to the low energy Lagrangian there. Okay, and the one thing we didn't actually explicitly talk about was how in the chiral Lagrangian, how do we actually do anomaly matching? So this is something I said we left as a aside, but there's a nice, beautiful story, for example, in Georgia's book, which tells you how to derive that pi FF tilde coupling in the standard model, and that comes from anomaly matching of the chiral symmetry in the QCD theory to the chiral Lagrangian. Once we include the axion, you do the exact same thing, but with this Lagrangian and you'll find that you also get these axion-photon interactions by matching anomalies between QCD and the chiral Lagrangian. Okay, how many people have seen Tufte anomaly matching and pi FF tilde? Yes, Ed has seen it. I'm contemplating if it will be a very long detour to talk about this. Let me just say very quickly how this works is that in QCD, let's do the chiral anomaly. This would be a very cartoonish version of anomaly matching. But if you do chiral anomaly, and we like trying to match the anomaly between QCD, the QCD Lagrangian and the chiral Lagrangian. And in QCD Lagrangian, we would do a chiral rotation of the partition function. And so essentially, we would calculate something like d mu j mu 5, and we said this would be proportional to FF tilde. So this would be a calculation of the anomaly in QCD. We could calculate it using triangle diagrams, for example. We put a j mu 5 current here and 2 photons here, and you calculate this triangle diagram. You have to be careful about regulation and so on and so forth. So this is a standard QFT textbook calculation. in Peskin and Schroeder, for example, that in a perturbative theory you can calculate what the chiral anomaly is, and the measure of the anomaly is that under a chiral rotation, what you measure is the divergence of the 5 current. If it was a symmetry, if it was not anomalous, you would get 0, but you get FF tilde. The way it's reproduced in the low energy theory is that pi 0 goes to pi 0 plus whatever you rotate this angle. So if you did the chiral rotation by an angle alpha, uh, that is implemented in the chiral Lagrangian by pi 0 shifting to pi 0 plus alpha. That is the point. That is the whole point of a Goldstone boson. A Goldstone boson is like doing the symmetry itself. The phasing symmetry in the original Lagrangian acts as a shift symmetry on the Goldstone Lagrangian. And so if we were to match this anomaly, that if we were to ask that under a chiral rotation, we produce a term that's proportional to FF tilde, the way to match it in the low energy Lagrangian is that we have a term like pi 0 FF tilde, and under the shift, it goes to pi 0 plus alpha FF tilde. Okay? So the existence of these couplings, pi 0 FF tilde or AFF tilde, can be deduced by anomaly matching between a perturbative Lagrangian and the chiral Lagrangian. Okay? This, very loosely, these are called West-Zumino-Witten terms. So, for example, Georgia has a very, very nice description of this physics in his book on weak interactions. But you'll find this anywhere else which does chiral Lagrangian. So the coupling of axions to photons or gluons can be deduced, usually can be deduced in the UV theory and perturbation theory. With the chiral Lagrangian, you can even use anomaly matching just like you would do for pions. Or you could put the axion in the mass matrix and do chiral Lagrangian using the mass matrix of the quarks. Okay, so this particular EFT for the QCD axion applies to any given UV completion you can think about. What we asked for from the theory is that we had some in the UV, we had some symmetry called the U1 Peccei-Quinn symmetry that was spontaneously broken at some scale FA. And this U1 Peccei-Quinn symmetry had an anomaly with QCD such that we actually got this coupling. We may or may not get this coupling, depending on what our UV theory looks like. But if for it to be a QCD axion, we certainly want it to be anomalous with QCD because that we want to eventually relax the theta, the QCD theta angle. Okay, so every kind of axion model has this feature. There's a U1PQ, global symmetry, anomalous, but anomalous with QCD. Spontaneously broken at some scale, FA. And the low energy description of that of this of the whole setup is this Lagrangian, which eventually gives you the Lagrangian in the pion. Okay. Any questions about this so far? Yes. So, so in simple models, we can say, for example, if you have, let's say you have a U1, the spontaneous symmetry breaking is happening by some scalar, complex scalar field, and there's a Wien bottle potential for this, right? So let's, the next thing, yeah, so let's do this. So there's a complex scalar, phi. Under U1PQ, it just rotates as usual e to the I phi times alpha times phi, right? And you can have some symmetry breaking potential, this potential, such that the symmetry is spontaneously broken. So the symmetry breaking scale typically would be something like, let's call it capital FA. and you ask what is the periodicity of the Goldstone boson that lives on the circle, that's 2 pi Fa. Right. So there's a natural relation between so if you parameterize this, not you can parameterize this as real plus imaginary, but you can also parameterize this as rho e to the I A over F around um, the typical parameterization around the minimum of fluctuation would be something like this, and the periodicity of the axion field would naturally be the web of this scalar field. Question, yes. So yeah, let's write on an explicit Lagrangian in a second, and we can write it down. Yeah. There's another question. Do you have a question? It's sorry, what? Because it's one loop exact. Um, yeah, yeah, and yes. Let's say. So when Tuft gave his argument, there was a very nice argument saying that what you can imagine is, let's say there's an anomaly like this. There's an anomaly in QCD with QCD or QED chiral anomaly. So you couldn't gauge the J mu 5 current because it's not conserved, so that's an obstruction to gauging. But let's say you add some spectator fermions, something which is not charged under QCD, so it doesn't participate in confinement, but it serves to cancel this anomaly. So there's extra fermions that are just fake fermions. They just cancel this anomaly. In this case, you could gauge this J mu 5 symmetry as well. So you have now a gauge theory with some spectator fermions that is anomaly free. So it's a consistent theory. Let QCD do whatever it does, and let's ask about that gauge symmetry in the low energy theory, including the spectator fermions, and so it should still be anomaly free. So that means when you remove the spectator fermions, the theory should have the same anomaly because the spectators are not doing anything. And so the fact that anomalies are, I mean, it shows, yeah, anomalies are not really perturbative quantities. They're non-perturbative quantities, as this sort of various ways of looking at anomaly shows you. One aspect of that shows up in perturbation theory as being one loop exact. But the power of anomalies is that you can match anomalies across threshold, and they're not affected by dynamics like confinement, or strong coupling, things like that. So that is how the chiral anomaly the anomalies played a strong role in deducing that the low energy theory had to be that of a chiral Lagrangian, and it couldn't have been anything else. Sorry, what was I? Oh yeah, chiral transformations. Yeah, so I'll give you an explicit version of this model in a second and give you the chiral transformation properties. Before moving on, let me just say one thing quickly about the conditions of quantization of the standard model. So here's a question. What is the gauge group of the standard model? This is now probably a famously trick question, but who wants to take the bait? What is the gauge group of the standard model? That's not the answer I'm looking for. Give me the naive answer first. You're too clever. No, you're right. So maybe some of you have heard this story. It's not that the standard model gauge group is not determined up to this factor that Anne is referring to, this factor gamma, which gamma could be so people usually say gamma could be Z2, Z3, or Z6. So the standard model gauge group could look like any one of these things. I should say as a general philosophy, the gauge group of anything is never fixed. Gauge symmetries are things you can always introduce, and you could actually you could decide that the standard model gauge group is anyway. So you could always invent gauge symmetries. Gauge symmetries are redundancies of your description. If you find some other description more more convenient, you could add gauge symmetries as you feel fit. as we did for the particle in a circle. We could have just worked on the circle, never talked about gauge symmetry, or we could work on the real line and we said there's a discrete gauge symmetry there. So if somebody asks what's the gauge symmetry of the system, that does not have a well-defined answer. It depends on who's, it depends on you. You can choose whatever gauge symmetries you want. The idea of this particular Z2, Z2, Z3, Z6 is the idea that, at least if you look at the standard model particle representations, even though we have, for example, quarks and quarks in electric charge 1/3 integer, if you actually look at gauge invariant operators or color singlet operators, they all have integer charges. So the conditions on quantization of charges, electric charges, for example, in the standard model, as applied to asymptotic states, which are color singlet objects or gauge invariant objects, is actually, as far as we know, the quantization of electric charges in integers, where the only well-defined way to talk about what electric charges is to ask for objects of which are asymptotic states or color singlets in this case. Okay, and so if we discovered a color singlet SU2 singlet charge 1/3 object, then we would then deduce actually the electron does not have the fundamental unit of electric charge. It has 3 times the fundamental unit of electric charge. But as far as we know, the electron is the fundamental unit of electric charge at the moment. And if the standard model gauge group was this SU3 cross SU2 cross U1 mod Z6, then this would be a requirement on that theory that you could not have a charge particle charge 1/3, just a color singlet or charge 1/3. Okay, so these discrete quotients tell you which representations you can have or not have. These discrete quotients also tell you what anomaly coefficients you can have with the axion with the photon, which is perhaps not surprising given what I told you. The axion-photon coupling arises from, say, integrating out some charged particles. If the charged particles have some restrictions on what their charges could be, you have restrictions on what the anomaly coefficient can be. Okay? So just in the standard model, E minus 2n over 3 should be an integer if this gamma is Z6. And you could derive similar quantization properties of, similar quantization conditions on these coefficients for other values of gamma. Okay? So if we saw the axion photon coupling is the way we would very likely discover the axion. And then if we had the infinite amount of money that was offered to us yesterday to build an experiment to actually measure E over n, so we can measure E and n, and we can actually deduce whether or not this is true. E minus 2n over 3 is integer or not, say to 10% or something like that. Then we would learn something about the actual gauge structure, the fundamental gauge structure of the standard model. We would learn that, let's say this was not an integer, we would learn that electron is not the fundamental charged object in the standard model. This we are learning from building a cavity experiment, this big cavity experiment on a tabletop. The particle which has charge 1/3 could be living at 10 to the 12 GeV. So there's no way directly you would ever measure this, but just by measuring these anomaly coefficients, you'd be able to tell arbitrarily UV spectrum of the standard model in principle. So measuring these quantities, while it's hard, it's a super important target. With a mild amount of optimism, we'll discover the axion in the next few years. And then the super important target would be to actually check what E over n is. And that will tell us super important information about the UV structure of the standard model. Okay? Questions about that? So in particular examples, you can actually learn a lot. You could actually check whether the axion comes from a grand unified theory, or you could check from whether axion can be embedded in various kinds of string theories. So it's a remarkable fact, and it again boils down to the fact that anomalies are robust quantities and can be matched way in the UV and way in the IR. So you can match anomalies in your 20 centimeter cavity experiment and match it in your theory at the Planck scale. And anomalies are integers. Integers have no option to run. Integers stay integers, and so you can actually deduce. There's this very tight connection you get between a far UV and far IR when you're matching anomalies. And so whenever you have such a tight connection, you can directly get experimental implications for very far UV theories in your model. So it's a very powerful probe of UV physics indeed, which again, people probably knew. Most people who worked on axions maybe knew it in the 80s, but it hadn't been emphasized until a few years ago how powerful this probe is. Okay. So let me flesh out this model that I just wrote down one part of in the well, maybe modes are interesting too, but models is what we want to talk about. So the one of the simplest examples of a model class is called the KSVZ model, where we can write down a renormalizable Lagrangian. So in some sense, the UV completion of this axion gluon interaction I just erased, and see how the structure arises. So what we do is we add to the standard model these following particles. And under the SU3 gate symmetry, we add, what should we call it? Let's call it psi. And we add just a color triplet and a color anti-triplet under SU3 color. And under the, we impose a global U1 Pechequin symmetry, which prevents us from writing down a mass term for these particles. So we could take it many different ways. We could take it 1, 1, -2, something like this. Okay. So the global PQ is imposed so that one that it would actually have let's do this actually. That might not. It would actually have an anomaly with QCD. So here we've only charged the only U1 PQ charged object is a color triplet. It's a wild fermion. This thing is not U1 PQ charged, so there's an anomaly now between U1 PQ. So this definition of this global symmetry U1 PQ times SU3 color times SU3 color has a triangle anomaly. In other words, the U1 PQ is ABJ anomalous with QCD. That is the structure we wanted. So far so good. We can't write down a mass term that preserves U1 PQ as we promised. Indeed, our theorem stated that we couldn't do that. But we can write down a term in the Lagrangian which looks like, as I call this capital phi straight now. And then there's some potential for phi, which is again U1 PQ symmetric and is such that it leads to spontaneous symmetry breaking. Okay, so maybe we can get something like. Okay, so a very simple model, just added one pair of wild fermions and one scalar, and this is the global symmetry assignment. When I break this, when I go below the scale of spontaneous symmetry breaking, I get the Goldstone plus the standard model, and indeed you can check that the fact that U1 Pechequin is anomalous means that I get a coupling A over FA GG tilde as the effective Lagrangian below the breaking scale. Okay. Depending on the model I want to build, I could also give these particles SU2 cross U1 charges. So the simplest KSVZ model, or sometimes people just call it the KSVZ model, but it's probably in the same class as KSVZ models, is these models where you can also give these guys electric charges or hypercharge or SU2 charge. And then you would also generically you would generate terms which are also A W W tilde, A hypercharge tilde. Okay, so the simplest model doesn't do that, but that's not, but that's by, so E equals 0 for the simplest model we wrote down. But that's by no means the only possibility in this class of models. Okay, any question about this? Yes. Yes. Yeah, that's a very good question, and indeed, there are some simple benchmarks you should write down. So maybe I should repeat your question for everybody. Um, yeah, let's do it here. So that typically when you see these plots uh, uh, for axion photon couplings, you again the plot that I drew. Typically you have GA gamma gamma, which was something like E over n minus 1.92 times whatever. Okay. Small fa. So oh, I forgot to tell you one thing which I shouldn't do now already. So for the QCD axion, actually, we also, one thing I didn't tell you is the relation between the mass and the coupling constant. So let me tell you now, and so that I need that now anyway. So we actually did all the work to calculate what the QCD axion potential is. So if you remember, we said the theta dependence of the chiral Lagrangian was something like something like this. But where theta used to appear, what appears now is axion, oh God, factors of 2. Let me check that out. Okay, don't quote me on factors of 2, but where theta appears now appears this quantity NA over FA. Right? We had theta FF, theta GG tilde, but now we said we produce an anomaly, and the anomaly with QCD we parameterize as this quantity integer n. And so instead of theta, we get NA over FA. So we know what the axion potential is right away from this. We replace theta by theta NA over F. And often you would call, so I should really remember the factors of 2 here, but often, Ed, do you remember the factor of 2 here? I think this is okay. This is not NDW, this is 2ND. Yeah. Yeah, that's why it's annoying. Is it NDW or is it 2NDW? Here it's NDW, which is 2n, right? Okay, let's not worry about factors of 2. They're not hard, but it's just I don't remember them because off my top of my head. But FA is defined as, well, let this be a lesson for you. There is a factor of 2 floating around in these definitions here, which is tricky. So make sure you got that right when you actually look up formulae. It's not really tricky. I just don't remember it. And so you can actually write down the axion. So this potential you can expand for small values of axion mass to quadratic, small values of axion field to quadratic order, and that will give you something like m. So V expanded for small values will give you ma squared, a squared, and then so you can read off what the axion mass is looking using this equation, and you find that the axion mass is this quantity. Okay. This when you expand this just gives you a squared over f squared, and so you get something like f pi squared m pi squared times a squared over f squared. And so that's why you get the axion mass. It looks something like this. Okay. How many people have seen the axion mass formula before? Okay, maybe a few of them. So the idea is for the QCD axion. If you tell me what Fa is, the small fa, I already know what the mass is. Okay, so let's write it out more clearly then. So if in these plots where we're plotting MA versus GA gamma gamma, where GA gamma gamma is defined to be E over n minus 1.92 alpha electromagnetism divided by 2 pi small fa. GA gamma gamma depends upon these discrete values E and n, and then this coupling constant 1 over fa. But the QCD axion has a relation between fa and ma. So that gives us a line in this plot for every value of E and n we can plot. So for every E and n, we get a line. So E over n equals 0 would give us one line. E over 8/3 will give you a lower line. So for a given model of UV model of the QCD axion, the coupling to photon can be parameterized as just these lines. And often you would see a QCD band being plotted where people have made arbitrary choices of what reasonable values of E and n are compelling models. But as Anne was pointing out, you could take E to be whatever you want, and you should really try and explore the entire parameter space. I should say these are, when you see these plots, these are log-log plots. So to actually get somewhere here, you would have to add a color triplet with charge 10 to the 6, right? So would you say this is a compelling model that you rule out or not? Then okay, that's a question of taste. So to actually get exponent to very far from these plots, people have built these so-called clockwork models. But exactly designed to try and get you much further from this, to qualitatively expand this QCD band to cover the entire. But these models the model building required to get something starting from a reasonable looking model to something that has this huge charges requires a bunch of structure. So it's not, while you're right, the QCD band could be whatever, we don't know. There's sort of a lower bound because there's this irreducible contribution. So unless you, well, I guess there's not one, because you could take E to be 192 and N to be 100, and then you could cancel it to more and more loops, but then it starts looking, again, not very compelling. So there's really, really 8/3 or somewhere around E over N equals 2 is probably the lower end of this, where you would say below that is probably hard to do and you're really tuning things. You can increase it, but again, increasing it qualitatively beyond E over N of 10 or something then starts looking not very compelling. So typically people expect the QCD axion to live in a band, but you should be aware of what model dependence comes in through this parameter. Okay. Question, yes. Sorry, louder, please. No. This is just the z is mu over md. So this is something we know, which is a 0.5 or something. So we know what z is. So just any other questions? Okay. So this is an example of the KSVZ model. There's a standard other example called the DFSZ model, and also there are many variants of these that one could build. Um, there's models that use there's a nice model which involves compositeness. So the idea where just like pions and eta prime uh, behave kind of like the axion in the chiral Lagrangian, maybe you have some physics in the at the scale Fa, which is confining dynamics of a new gauge group, a dark QCD, and it has its own chiral Lagrangian, and it's one of its mesons, one of its pions is the axion, and you can build reasonably elegant looking models and field theory looking, which look like that, and so those are again a variant of these models that we're talking about. Below the scale of Fa, again, that looks exactly like what we've been talking about. It looks like this effective theory for axion, gluons, photon coupling. What I want to talk about instead of these models is uh, a couple of qualitative aspects of the axion solution with a strong CP problem. Um, Again, but if you're interested in model building of the QCD axion, it's well worth being aware of the classes of models people have already thought about, and these three classes are probably a good starting point. Um, so there's so-called quality problem, sometimes called the PQ quality problem, sometimes called the axion quality problem for axions, for the axion solution. So all the things we've said so far for the axion solution have been positive. When we were talking about the discrete symmetry CPR parity, we kept saying it's terrible, one loop, two loop, we have to calculate all these things and never works. We've been saying all positive things about the axion so far. The biggest criticism the axion models face to solve the strong CP problem is the so-called quality problem. Who can tell me what the quality problem is? Okay, yeah, that's basically correct. So our potential, yeah. So this is the potential for the axion. If you plot the potential for the axion, we've done this previously, where we looked at the energy of the energy as a function of theta, so which is the same as the potential for the axion when we think of theta as the axion, and we find that that this potential is minimized at axion equals 0. Right, so this minimum is axion equals 0, and this is not just a consequence of this particular model or the approximation scheme. This is guaranteed to be true by a theorem by Waffa and Witten, who showed that if you ignore CP and parity violation by weak interactions, which is a very good approximation at QCD scales, the minimum of the potential would be at axion equals 0, at theta equals 0. Okay, and there's a very general, elegant argument that they gave. Yeah, so it's worth looking at that paper. But so what we're told is that, okay, in the absence of other CP violating contributions or the other PQ violating contributions, what QCD gives us is a minimum at theta equals 0. And so this is sometimes, by the way, said that the axion relaxes the theta angle dynamically to 0. At the minimum, at axion equals 0, we have no longer theta angle. The EDM, neutron EDM would be whatever the value of the axion is at the minimum. Okay, and this is coming from this potential coming from QCD. Um, if there were other potential terms that were explicitly violating the symmetry, so for example, in our KSVZ model, we wrote down a potential which looked like phi dagger phi minus v squared. So this obviously has the U1 Pechequin symmetry built in. And anything that you can write down with phi dagger phi is U1 Pechequin symmetric. But you can also imagine writing down terms which don't involve um, but let me write down what people usually say and then say what I think is going on. So you can write down terms like, say, at the Planck scale, some term that looks like this. This term is not allowed by the PQ symmetry. This will break the PQ symmetry, and in particular, it would produce f to the n, m Planck to the n minus 4 cosine axion potential. Okay, you replace phi by f e to the I a over f, and then capital F, capital F. You'll get some term like this. So if you had explicit breaking terms of the PQ symmetry, remember it's a global symmetry, nobody forces you to not write these down. You have to impose a global symmetry. Then you would get extra terms which look like this, which are not coming from QCD. They could come with an arbitrary phase, and they could move your potential to some other value, a not equal to 0. So if you minimize, so this could be some complex coupling, right? So this could be some coupling y. So this would be some random a plus phi over f. The minimum of this potential that you generate from some new PQ breaking effect and the minimum of the potential from QCD have no reason to be aligned with each other at all. And so you will generically shift the minimum away from axion equals 0 to some other value of the axion field. Okay. Neutron EDM tells us that this value, a over fa, should be less than 10 to the minus 10. So you don't have that much room to shift the axion minimum away from the origin at all. And so that puts a severe constraint on what symmetry breaking effects you can contemplate for two reasons. One is that the coefficient of the potential from the QCD is that of the order of QCD scale. F pi, M pi are both order 100 MeV. Whereas this UV potential could come from any from a UV scale, and it doesn't have to be similarly suppressed. So in principle, if you contemplate writing operators like this, you find that n has to be bigger than 14 for some values of some canonical values of fa that you might care about. So the suppression from f over m Planck has to be 14th orders before you can be viable. We can have a viable model. Okay, so this is the so-called quality problem for the axion, where higher dimension operators like this could potentially, so even dimension 6, dimension 8, dimension 10 operators could spoil the solution. And so it starts looking like Nelson bar in that spirit, saying, well, let's write on the first operator. People usually write first operator with dimension 5. Actually, you should write phi squared, m Planck squared, phi squared. You shouldn't start with a higher dimension operator. You should start with the lower dimension. So there's a hierarchy problem for phi in principle if PQ is not a symmetry. And you keep going, and you say, well, you have to kill everything until Z4, until dimension 14 in order for this to be a viable solution. So maybe that makes it less compelling. That is the standard argument. And you can do model building to try and generate some structure such that this symmetry, you can impose a Z14 symmetry. Again, doesn't sound as compelling as what we were saying before. To get rid of this problem. Okay. Question? Yes. Good. Yes. So if you're just talking about an ALP rather than the QCD axion, uh, the web would not be the strongest constraint. However, notice that this also produces a mass for the axion, right? So the effect is to move this, and also, if I make it more dramatic, to make it heavier, potentially. Right? So if you really added just the dimension 6 term, the mass of that axion would also be, it would not be micro electron volt anymore, right? So the dominant effect turns out in the QCD case, because the web has to be so small, is the moving of the web. But if you just add mass terms, you would also just, you have no longer the pseudo part. The Nabu-Goldstone boson is very far from being a Nabu-Goldstone boson, so you just have a heavy axion now. So for experimental reasons, if you might care about an ALP showing up in tabletop experiments, this is still a worry, but maybe a different kind. It's not the 10 to the minus 10, you're right. Good. So in the last part, let me tell you uh, a class of models in which the violation of um, this global symmetry is without adding very much structure, like maybe new confining sectors and some number of extra degrees of freedom and or Z14 global symmetries. There's just uh, a very good protection of the PQ symmetry, the low energy PQ symmetry from these potential effects from the UV. And these, so for one, from the bottom up, this is what makes these extra dimensional axions compelling. If axions come from extra dimensional theories, then they have a protection against the quality problem. But also, from the top down, we expect if you believe string theory is the correct theory of quantum gravity, you believe that the UV theory lives in higher dimensions, and string theories naturally give you candidates for axions when you compactify 10D compactify a 10D theory down to 4D. So from the top down also, the UV theory naturally gives us these candidates which could solve the strong CP problem. So these become a nice compelling thing to think about. So what we're going to do is to just work in a toy 5D example and to see how axions come about uh, in, uh, in extra dimensional theories. Whenever you have gauge fields, a gauge theory in extra dimensions, you potentially have axions in the 4D effective theory. And in fact, some of our hard work thinking about the particle on a circle and the Maxwell 1+1 Maxwell theory will pay out, because we'll see the structures parallels exactly what we talked about in that context. Okay. So here's the 5D theory. There's a 5D Lagrangian for my theory. So I have a U1 gauge theory. FMN is the gauge field strength for that. And my theory is defined on the fifth dimension is a circle. So let's parameterize by the coordinate y. So let's say y goes between 0 and 2 pi r. Okay. So this is some 5D theory. If I go below the usual story is that I can do KK decomposition of all my fields on the circle, and the low energy theory is a 4-dimensional theory with a tower of KK modes. Uh, I can add charged particles with some mass charged under this U1 symmetry, and in the 5D theory, and in 5 dimensions, I can write on an extra term. Using the 5-dimensional epsilon tensor, which looks something like this. So in 3 dimensions, these are the Chern-Simons theories. This is the 5-dimensional version of a Chern-Simons term that you can write down. There's no theta term that you can write down in odd dimensions. the analog of the theta term in odd dimensions becomes this Chern-Simons-like term that you can write down. And the um, yeah. Okay. So in the 4D theory, um, what we will have are is a tower of states. And let's see what the tower looks like. There's a charged. So this is the energy. This is the mass of the particles. So we have some field psi, which is charged. Well, let's talk about the gauge bosons first. So we have a let's say this is 0. So we'll have a 4D gauge field A mu. That is the 0 mode of the photon in 5 dimensions. We would have a tower of spin 1 massive particles. So this would be order 1 over r mass for each of these gauge bosons. So we have a massless photon, the gauge theory, but then a tower of massive excitations. So these actually have 3 degrees of freedom, right? So let's say. So let's show the degrees of a degree of freedom by these 3 arrows. So these together give me a massive spin 1 particle in 4D. And these are the 3 degrees of freedom. For the massless guy, I only have 2 degrees of freedom at the 0 mode. Okay. Where do these degrees of freedom come from? The third longitudinal degree of freedom for these massive guys. Can someone tell me? So in the 5D theory, I had AM, which was a 5-dimensional gauge field. Where are these extra degrees of freedom that I need for making a massive gauge boson in 4D coming from? Indeed. So there's A5. So we break AM into A mu and A5. And the idea is that if we KK decompose A5, then we'll also get KK tower for A5, which you can think of as the longitudinal mode for the photon. And so all the KK tower of A5s is eaten by all these KK modes of the photon. But then we're left with these guys that together make a consistent field theory, a massless photon, and we get a 0 mode for A5. Okay. So the A5 0 mode is an axion. So this is the origin of an extra dimensional axion. One of the polarizations of the 5D photon in the 4D actually behaves like an axion. Okay, so all these words we were saying, we should think of the axion as a gauge field. It has the same analogous properties as a gauge field. Here, the analogy is super precise. It actually lives as a gauge field in the 5-dimensional theory. Okay. There's another way to write the same. So we could write A5 as the axion, but there's a slightly more invariant, gauge invariant way of writing down the axion field in 4 dimensions, which is this holonomy of A around the circle, the 5th dimensional circle, is a 4-dimensional field, which is the axion. So this should now remind you of what we were saying about when we're defining a theory in a 1+1 in a 2D example. We compactified it on a circle. We got a 0+1 dimensional theory, and we got Q of t as our effective theory. So remember, Q of t we defined as something like as a quantum mechanical variable when you compactify a 1+1 dimensional theory. Here we're compactifying a 4+1 dimensional theory, so we get a 4-dimensional field, which is exactly the same structure as our particle in a circle. We briefly talked about the shift symmetry of this Q of t deriving from a one-form shift symmetry of, sorry, question. Yes, yes. This is a 5D. Yeah, it's a 5D one form. So in a particular gauge, it's really just A5, but you can talk about it in a slightly more gauge invariant ways. Um, so let's look at the symmetries. In the 5D theory, we have the U1 gauge symmetry. So what we would have is in particular a U1 U11, so one form global symmetry. Um, any Maxwell theory in any number of dimensions has a U1 one form global symmetry potentially. So uh, this is broken by the presence of psi. So it's an approximate symmetry at the moment, but let's ignore psi for a second and say in the 5D Maxwell theory, we would have a U1 one form global symmetry, which is a global symmetry of the theory. And when you compactify in 4D, you get a U1 one form symmetry of the 4D Maxwell. So you get the photon Lagrangian, and the photon part of the Lagrangian still has the one form symmetry, and you get a ordinary zero form symmetry of the axion. Okay, so the U1 Peche-Quinn, which is the axion, which translates into the axion shift symmetry, the symmetry that we are trying to track, whether or not we can have extra potential terms for the axion. In this case, that global shift symmetry is coming from this one form higher symmetry in the 5D theory. Okay. Notice that we didn't have any other option to write any other terms in the 5-dimensional Lagrangian. Gauge, we just wrote down every term consistent with gauge invariance. We did not impose any global symmetry. There's no local operator that you can write down beyond the ones we've written down that would violate this U1 one form symmetry further. So the whole protection of extra dimensional axions comes from this fact. Sometimes people say it comes from a gauging of the symmetry in the 5D, but that language is really confusing. You don't gauge anything. Global symmetries are global symmetries always. So there's a global symmetry in 5D theory, which is this one form global symmetry that descends to a zero form global symmetry of the axion. Local operators don't break this one form global symmetry in the Lagrangian, and so this is why this one form global symmetry is better protected than just a random zero form global symmetry in the quantum field theory, and that is the protection that you get that the axion inherits. Okay, so why is the extra dimensional axion better? Because the shift symmetry is actually a one form symmetry in extra dimensional theory, which local operators can't break, and it's naturally exponentially small breaking of these symmetries that you get. Questions? I do want to give you a 5-minute break before Ed starts talking. So, I wanted to show you um, what the breaking looks like. Let me tell you, and then leave it as an exercise. And in fact, I think Matt Reese's lecture notes actually go over the breaking of this one form symmetry. So the one form symmetries we said are broken by presence of charged particles. So this one form symmetry is not exact. It's approximate because we have these charged particles that Wilson lines can end on. So this breaking, while it's not explicit breaking in the Lagrangian in any sense, it is a breaking effect. And so the question is, how does it show up in the low energy Lagrangian? So let me give you a qualitative argument to show why it's exponentially small, and then refer you to Matt's notes to actually you can calculate it in great detail in 2 different ways, and actually it's quite satisfying. Poisson makes an appearance in that calculation. So it's a very nice calculation. But let me give you a physics heuristic reasoning for why the symmetry is protected. Okay, so the idea is that the axion, this one-form global symmetry is broken by the presence of this charged particle. Okay, the charged particle has some mass, um, and we want to understand what is the consequence of that breaking in the 4D effective theory. What mass does my axion get? What is the going rate for that? So if you look at the extra dimension, let's think about the fermion field. You can show that you can choose a gauge where you can do gauge transformations to move the axion to any part of the extra dimension you want. So what you can do is you can say, just like we were only talking about the theta term in 4D, we could say along the circle, the whole dependence on the axion is that when the charge field psi goes to this point, let's say it's 0, y equals 0, is e to the I a psi of y equals 2 pi r. Okay, so just like we argued for the theta term, exactly analogously, instead of thinking about the theta term as a term in the Lagrangian that you wrote down, you can say the whole or an axion as that. So this is just the same as e to the I a, by the way. Instead of thinking of the axion as something, the axion photon coupling as a term in the Lagrangian, you could move it into the boundary condition for the fermion. So you say that the fermion, the charged fermion, when it goes around the circle, doesn't come back to itself, but comes back to itself with this twist. Okay. So what this tells us is that the modes. So if the fermion is, if you calculate a fermion loop here, that fermion loop is never sensitive to this actual twist in the boundary conditions. It never even sees the twist. So the fermion loops that will be sensitive to the axion value at all are fermion loops that will go around the extra dimension. So the sensitivity to the axion value, a constant axion background, is only to loops which wind around the extra dimension. Again, it's not exactly analogous, but it's very close to the idea that when we're talking about the instantons, the theta angle showed up only in the winding sector. So whenever we had one winding, that was proportional to e to the I n theta. And if a path does not wind at all, the instantons didn't show up. So this is again saying the axion, which is just the winding of this, just like the theta angle for this theory, only shows up in these winding trajectories for the fermions. So we have a fermion to be able to contribute to the axion potential, to be able to be sensitive to the theta angle or the axion. It has to wind around this extra dimension. We can estimate a massive fermion. What is the propagator for a massive particle to go a certain spatial distance? And so, if the mass is much bigger than 1 over r, this propagator, a spatial propagator, goes like the Yukawa force, and so this goes like e to the minus mass times r. Okay, so it's a heuristic argument. It can be made more precise, and but the idea is this: that the only thing sensitive to your axion value, a constant axion value, is trajectories of this charged particle that go around the circle. Going around the circle for a heavy particle costs a lot of action. The classical action for that goes like e to the minus classical action goes like e to the minus mr. Okay, so it's only these very suppressed configurations that would be sensitive to the axion potential. So your axion potential would naturally be of order e to the minus mr times cosine A. Okay, so again, this is not surprising if you remember. For our particle in a circle, v of theta, there was some omega. So E of theta was omega over 2 plus k cosine theta e to the minus s classical. Okay, so just compare this with that formula where now the theta dependence is the potential for the axion. If the potential for the axion comes from only semi-classical trajectories with a large action, then the theta dependence in of the energy is exponentially suppressed. And that's exactly this fact here, that the theta dependence here is exponentially suppressed in the classical action of this heavy charged particle having to go around the circle. Okay, and so this is the braking effect. All we have to ensure is that there are no light particles for which there is no suppressed action. As long as this condition is true, the mass of the particle being much larger than the size of the extra dimension, this exponential suppression is robust. There is nothing else that's sensitive to the theta angle. So we can then flesh it out into a really full-fledged model and ask how generic this is, and how easy it is to get this exponential suppression or not. But this is the toy. This is the toy version of the mechanism that's undergoing stringy axions. When people say stringy axions give you a very high quality axions in 4D with a potential that's exponentially suppressed in the volume of the extra dimension in some units. Okay, so you see that e to the minus mr in further higher dimensions would become volume of the whatever extra dimension you're talking about in the typical units, in typical string units. So large volume extra dimensions compactification give you axions which are very high quality, and so those are very compelling models for solving the strong CP problem. I'll stop there. Thank you.